Alright, so in this video we're going to go back and we're going to kind of review quantum theory, the Bohr's model, and now apply some mathematics to it. So hopefully it'll all start to come together after hearing it now probably for the third time. So again, remember waves, we need to know a little bit of something about a wave. The wavelength, so the distance between one wave cycle and is related to the frequency. So frequency is how frequent the wave is, which is related to the energy, which is related to the color. They're all sort of intertwined. So something that has a small wavelength, let me just zoom in a little so you can see that a little bit better. Something that has a small wavelength has a very high frequency and therefore is very high energy. And the wavelength correlates to the color or the type of wave it is, and we'll look at that in a second. Something that has a large wavelength has a very low frequency and therefore a low energy. So let's take a look at the electromagnetic spectrum quick, and then we're going to learn how to calculate actually the mathematical relationship between frequency and wavelength. So the electromagnetic spectrum, you can see here, are light waves that are just different sizes, so we give them different names. So ones that have a very small wavelength are like gamma rays, X-rays, and UV rays. And again, remember, if they have a very small wavelength, that means they have a very high frequency and they're very high energy. Whereas on the other end, we've got some large wavelengths like radio waves and TV waves and infrared. And those large wavelengths have a very low frequency and a low energy. And then a very narrow range of it is the visible light spectrum. Okay? And when we talk about atoms, in order to get them to release that light, okay, we plug them up to some sort of electricity and their electrons start jumping around like crazy and they glow light out at us. And the light that they glow out at us tells us something about the position of the electrons. Okay, so that's what this is. We've got a Bohr's model. All these little arrows and paths are called jump paths, and there's an electron, one electron jumping in all these different shells, and therefore releasing different wavelengths of light. So we've got infrared, we've got visible, and we've got UV. And every single type of atom releases a different type of light when it's excited because of the different arrangement of its electrons. Okay, so that's big picture. Now let's go and start to apply some math to it. So we have talked about the fact that frequency and wavelength have an inverse relationship. It means when one's big, the other's small. Right? So when the frequency is low, the wavelength is big. When the frequency is high, the wavelength is small. So I want to be able to calculate that. And in order to calculate that, we need to use what is called the wave equation. And the wave equation is that c, which is also known as the speed of light, is equal to wavelength times frequency. And the wavelength we already discussed is in meters. The frequency is in a unit that we call hertz, which is actually 1/2. So I'm going to do a quick sample problem here using a wavelength of light. So let me go under the Alamo, and we're going to do a quick sample problem with the wave equation. All right, so let's just look at our Bohr's model here, and we're just going to pick one, right? Let's pick 410. Now remember, that is in nanometers. And this is the wavelength. So let's calculate the frequency. Right? So C is equal to wavelength times frequency. C is the speed of light. It is always the same. It's never going to change. It will be provided to you on any test that you are asked to perform a calculation. It's 3 times 10 to the 8th meters per second. Okay, so it's a speed. It's how much distance you cover over how much time. So the wavelength, like I said, we're going to pick this one that's 410, and it's in nanometers. So wavelength is equal to 410 nanometers. However, if we're going to plug this into this equation, we need to have it in meters, right? Otherwise my numbers will be wonky. So I'm going to convert this from nanometers to meters. And I can do that by simply saying 410 times 10 to the negative 9 meters. Or if I want to write it in very nice, pretty scientific notation, I could say 4.1 times 10 to the negative 7th meters. All of these numbers are the same. However, I need to have it in this form or this form to plug it into my equation. And that will allow me to calculate my frequency, right? So if I want to solve for frequency, I'm going to divide by wavelength on both sides. And so I will get that the speed of light, 3 times 10 to the 8th, divided by the wavelength, which is right here, 4.1 times 10 to the negative 7th, is going to give me my frequency. So let me grab a calculator quick. So again, we've got to use our scientific notation key. So 3 e to the 8th divided by 4.1 e to the negative 7th gives me 7.3 times 10 to the 14th. 7.3 times 10 to the 14th. And that's frequency, and remember I said frequency is hertz, right? And that, remember, relates to the energy. So that's going to be the next step. So now I can go from wavelength of light to energy, or to frequency of light. And when we excite an atom, what we actually see, what we actually measure, is the light that comes off it. So that's why we've got to make these steps, right? So we're going to see and measure the light, and then somehow we're trying to figure out how the light coming off of it relates to the energy and the arrangement of the electrons. So the first step is to go from the speed of light to, or the wavelength to the frequency, which we've just done. So now the next step is here, and this is to go from frequency to energy. So we said that a wave that has a really small wavelength has a very high frequency. And a really high frequency means it has a lot of energy. A wave that has a really low frequency and is sort of a sluggish wave, it has a low energy. So the equation for calculating the amount of energy that a wave of light has is this. It's E, energy, is equal to H, which is Planck's constant. It's a known value, it never changes, times F, the frequency. So the Planck's constant is written here at 6.65 times 10 to the negative 34th, and the unit is joules times seconds. Okay? And the unit for energy is then joules. So the next step is we want to figure out the energy. So let me just go back to my sample problem here under the Elmo. So I have, this is my frequency, right? This is my F. So I want to know, well, how does that relate to energy? Remember, small frequencies have high energy, low have low energy. So I'm just going to say, well, I know that energy is equal to H times F. And H is always that weird number that will be given to you. And it's got this unit. Don't even worry about that, what it means, but we just have to have it there. And then frequency is up here. I just calculated it, 7.3 times 10 to the 14th. And it's in hertz. And I want to know energy, so all I got to do is plug and chug. Take 6.65 times 10 to the negative 34th and multiply that all by 7.3 times 10 to the 14th. Let's plug her in. 6.65 e to the negative 34th times 7.3 e to the 14th. And I get 4.9, we'll round it, times 10 to the negative 19th. So 4.9 times 10 to the negative 19th joules. Joules is the unit for energy. So what does that mean? What does that actual number mean, going back all the way to the beginning? What this means is that if we look at this electron right here, this electron absorbed 4.9 times 10 to the negative 19th joules from whatever source, electricity or heat or whatever. So it could jump from this energy level to this energy level. Then when it fell from what is its excited state back down to its ground state, it released a wavelength of light that was 410 nanometers that we could see. So we were able to see that wavelength and figure out how much energy it was for the electron to go from here to here. That's how we know where electrons are located in atoms. And because every single atom has a different arrangement of electrons, every single atom or type of element has what we call a different emission spectra. So if we look at an emission spectra, let's see if I can get it to actually come up here. Slide. This kind of slows down here. Let's just give it a second and see. There we go. So we see these lines of color that are a specific wavelength that correspond to that jump path. And so every single, this is for hydrogen, again we've been talking a lot about hydrogen, but we will see different ones for helium and neon. And in the lab on spectral math, you're actually going to interpret, visualize the spectrum, select one of the lines, and be able to calculate the energy of that jumping electron.